Hello students, I am Akhilesh Kumar Srivastav. I am presently working in ABS Engineering College, Ghaziabad. In the series of the data structure lectures, we have discussed about the quick sort process on the last turn. We will continue with the discussion, and today we will discuss about the time and space complexity of quick sort. We will see what are the different cases possible wherein the time and space complexity of the algorithm will have a change. So, the outline of today's lecture will be that we will first discuss about the quick sort process, then we will see what are the various cases in the quick sort, we will see the runtime analysis of the quick sort, we will see how to control the worst case, we will see how the partition can be done with the median element as a pivot and randomized quick sort. Finally, we will discuss about the quick sort's space complexity. So, now in the last lecture we have discussed that you can perform the quick sort with the help of the partitions, with the help of doing the partitions at various times. What does the partition do? It selects the first element or any element as a pivot. The comparisons are made around the pivot element, and we fix up the place for the pivot element in the sorted array such that the elements on the left hand side of the pivot element has the smaller keys than the pivot, and the elements on the right side of the pivot has larger element than the pivot. So, we find out the position of the pivot element in the sorted array such that all the keys or all the elements those are lying towards the left of the pivot element contains a smaller element than the pivot, and all the elements on the right hand side contains larger element than the pivot. So, this is the process of the quick sort. We have seen an example and we have done this. So, now once you are done with the partition, you perform the quick sort on the left part of the jth index element, and then you perform the partition on the right half of the j. For example, if this is the array given to us, wherein the index low is defined here, index high is defined here, you perform the partition and you get an index j. The position of the jth element has got fixed in the sorted array. So, you remain with two parts, one on the left and one on the right. The smallest index on the left hand part is low, and smallest index on the left, sorry, largest element on the left part will be j minus 1. Similarly, the smallest index on the right part will be j plus 1, and largest index on the right hand side will be high index. In case you take an example, numerical example, let us say we have been given an array which starts from index number 1 and it has the index up to 10, and the smallest index is 1 as low, highest index is high which is 10. Let us do the partition and let us say the position of the 6th index element gets fixed. So, j is 6 here. Now, once j has got fixed at 6th index, you have two parts in the array. One is ranging from low to j minus 1, that means 1 to 5, and the other part will be j plus 1 to high, it means index number 7 to 10. So, you will perform the quick sort on the left part, and then you will perform the quick sort on the right hand side as well. So, that is the principle of the divide and conquer. We have divided the array into two parts using the help of this partition algorithm. So, now this partition is done for the array which returns at j index. You perform the quick sort, you call the quick sort on a array that ranges from low to j minus 1, it means the left part, this is the left part, and then you perform the quick sort on the right part. A array starting index is j plus 1 and last index is high. So, you perform the quick sort on the left part and the right part as well. Now, this is the partition algorithm. In this partition algorithm, if this is the array given, we are assuming that this is the low index, this is the high index. From your side you consider an element which is infinite. Infinite is nothing but the largest larger element than the largest in the set. So, you set the last element as the infinite, and this is for the first execution of the partition only. It means first time when you are calling the quicksort, then you will be setting up last element as infinite. Otherwise, in all other calls of the partition, infinite will be taken by default by the algorithm. Now, this is low, so you start I at this index, you start j at high plus 1 index. Up to high we have the valid elements. So, high plus 1 is your assumed element or your assumed index where you have infinite. So, you set j there. So, I is initialized at the low index, j is initialized at the high plus 1 index, and then we are setting up the first element as the pivot. So, a low element, it means the first element here is actually taken as the pivot. After this, you do the pair of the operation, you increment I until you get a larger element than the pivot. If you have a smaller element, then you again increment I. So, you keep on incrementing I until you have a smaller element, and then once you find the larger element, you will stop I. Similarly, once the increment of I is over, you will decrement j, the j will move from right to left. It will keep on moving until you have a smaller element than the pivot. The moment you find the smaller element than the pivot, you will stop there. After this, you have to check if i's position is less than j, then you will exchange ai and aj element in the anticipation that the smaller element should come on the left and the larger element should go on the right. Okay. So, after this, you again repeat this process. So, you will keep on repeating this process by the time I is less than j. The moment I exceeds j, you will stop this operation and you will exchange the jth element with the pivot element in the array. The position of the jth element will be fixed and that will be returned by this algorithm for the quicksort algorithm to know which element has got fixed. Now, let us say we have the even partition of the array. Even partition means the partition of array took place from very mid. So, you can assume that the left hand side array contains n by 2 elements, the right hand side elements will be also n by 2. In the next partition, the division is once again in the mid. So, it is divided into n by 4 and n by 4 parts, and then n by 4 is again divided into the n by 8 and n by 8 parts, and we keep on, if we keep on dividing, so we have the part of array as 2 and 2, and then let us say it is further divided and it has 1 and 1 element each. So, once you have reached to the array which has single element, the further partition will not be required. So, you stop here and you start combining your solution. Okay. So, if this is the even partition in the array, in case you are dividing the array into the equal size. Now, in case we have the equal divisions, you can see that the partition algorithm will require theta n time in case you have n elements in the array. This quicksort will contain n by 2 elements. This quicksort will also have the n by 2 element array. In case you have to find out the time complexity of quicksort on an array of size n, let us say it is denoted by Tn. So, Tn is denoting the time complexity of quicksort of size n. When you are dividing this into two parts, n by 2 and n by 2, we will again perform the quicksort on n by 2 size and n by 2 size array. So, let us say Tn by 2 denotes the time complexity of quicksort on n by 2 size array. Similar will be here as well. So, you now have a recurrence as Tn is equals to Tn by 2 plus Tn by 2 plus theta n. Theta n is the complexity of the partition. This can be written as Tn is equals to 2Tn by 2 plus theta n. Theta n can be represented as C into n. Let us say we are assuming that the value of C is 1. So, we have simplified this expression and the simplified expression is this one, Tn is equals to 2Tn by 2 plus n. Now, to solve this equation or to solve this recurrence, what we assume that if Tn is represented as 2Tn by 2 plus n, then Tn by 2, when you apply the partition or you apply the quicksort on n by 2 size array, that will once again be divided into two parts of n by 4 and n by 4 size. So, this recurrence can be written as, for T n by 2, it can be written as 2T n by 4 plus n by 2. So, what is happening, you understand with this expression, that if here we have n, here we have half of the array, and this value is same as this one. Similarly, for T n by 2, this value has been halved, and then this value and this value are same. Okay, you put this value here, T n is equals to 2, T n by 2 is replaced by 2T n by 4 plus n by 2. Okay, if you simplify this, you get T n is equals to 2T 2 square T n upon, if you are writing this 4 as 2 square, and then you will multiply 2 with n by 2, that will get n, and another n is here also. So, you can write it as 2 into n. So, the expression actually has become T n is equals to 2T n by 2 square, sorry, this is 2 square and plus 2 into n. Can you say that whatever is the divisor of this or whatever is the power of this is the same as the power here, and the power is the multiplier of n here. If you further divide it by 2, again this will actually look like this, T n is equals to 2 cube T n upon 2 cube and then plus 3 into n. You do not know up to what extent you should actually divide it. Let us say we assume that we are going to divide it up to k steps. Okay. So, what will happen in the kth division? This 2 power k will appear, the division of n will be 2 raised to the power k, and the multiplier of n will be k. So, you have this expression. In this expression, we are assuming that the division will further not be required in case n by 2 raised to the power k becomes 1. In case this value is 1, it means we have a one size problem, then the further divisions will not be possible or further divisions will not be required. So, we are assuming that n by 2 raised to the power k is equals to 1. The same can be written as n equals to 2 raised to the power k. Okay. In case you take log on both the sides, then you will have log n is equals to log 2 raised to the power k. Let us say the base 2 log we have taken. This k will come on this side. So, this will be k into log 2 to the base 2. The value of k log 2 to the base 2 will be 1. So, this value is k, which is equal to log n to the base 2. So, the value of k has been decided as log n to the base 2. So, we are going to put all these values here. So, 2 raised to the power k, here 2 raised to the power k, we are actually making changes in this expression. So, this 2 raised to the power k can be written as n, you know it well. Let us see here, and then we have a T1 because n by 2 raised to the power k has become 1, and then k into n. The value of k is log n to the base 2, we have already decided. Here we have a multiplier n also, let us do it on the left hand side. So, the term has become n into T1 plus n log n. Can we write it as n? T1 means what? T1 means we have a one size problem. If we have a one size problem, it means we will go to the quick sort, we will check this condition and will terminate because this condition will fail. So, in one statement only, you will be in a position to know that quick sort has not to be processed further. So, the value of T1 is taken as 1 here. So, n into 1 plus n into log n to the base 2. So, the value of this can be written as order of n log n, because n log n is larger than n log n to the base 2. So, here the complexity can be written as n log n to the base 2, since we are assuming that the partition is taken from the very mid. So, this will perhaps be the best case. We will see other cases also, but this will perhaps be the best case here. Now, let us take some of the conditions. We will decide about the notations later, but let us say we have some of the conditions here. Let us say we have the equal keys in the array. The partition algorithm says that set the first element as pivot. So, pivot is 10, Partition algorithm also says we have a I here, we have a j. You increment this I until you find a larger element, or come back to the algorithm and see that this algorithm says that if the ai is less than pivot, so increment I. Similarly, if aj is greater than pivot, decrement j. What is the reverse meaning of this? The reverse meaning of this is if ai is equal to pivot, stop. If ai is greater than pivot, stop. Similarly for j also, if aj is greater than pivot, do not stop, keep performing j minus j minus minus. But if aj is equal to pivot, stop. If aj is smaller than pivot, then also stop. So come to this example, I has reached here, this element is equal to pivot, so we will stop. Decrement this j, this element is smaller than the pivot, stop, stop. So now I is less than j, I is 1, j is 9, so exchange these two, which will make no difference actually. 10 is replaced with 10, 10 is exchanged with 10. Again repeat this step, I comes here, this element is equal to pivot, we will stop. This element is equal to pivot, we will stop. We will exchange second and the 8th element because I is 2, j is 8 and I is less than 8, I is less than j. So we will exchange these two. Then again repeat the same step, I is incremented by 1, this element is equal to the pivot, we will stop. This element is equal to the pivot, we will stop. Now the position of I is 3 and position of j is 7, I is less than j, so we will exchange ith and the jth element. But after this you will again repeat the process. I is incremented by 1, this element is equal to the pivot, we will stop. J is here, this element is less than, this element is equal to the pivot, we will also stop here. Then again check the position of this 4 and 6, that is I and j, I is less than j, so we will again exchange these two values. Okay. Now after exchanging these two values, come here. We have reached at this position, this element is equal to the pivot, stop. This element is also equal to the pivot, stop. Now the I is 5 and j is also 5. That means I is not less than pivot. Since I is not less than pivot, so we will exchange j and the pivot element. So this element 10 and this pivot element, these two will get exchanged. By that the position of this element will get fixed. If the position of this element gets fixed, elements on the left of this will be less than this, element on the right hand side should be greater than this, but in this special case all the elements are equal. So we will perform the quick sort on the left part and then we will perform the quick sort on the right part. You can see that you had 10 elements and the index of the element that has got fixed is in very mid, so this best case actually has appeared. In the subsequent partitions also the middle element will be getting fixed, so the best case has appeared here. So you can remember that if the elements given to you are already sorted, that means this is the best case of the quick sort, and you can write the recurrence of the best case as 2t n by 2 plus theta n. So this is the recurrence for the best case of the quick sort. Now let us say the keys are in the ascending sequence. Okay, if the keys are in the ascending sequence, let us take the first element as pivot. This element is set as pivot I and this is j. Then we increment I till we get a larger element than the pivot. Yes, this element is larger than pivot, stop here. Now for decrement of j, j comes here, not a smaller, not a smaller, not a smaller, not a smaller, not a smaller. You will keep on decrementing this j and you are not getting any element which is smaller than the pivot. But when you reach to the first element, this element is equal to the pivot. So we have said in this algorithm also that in case you have the smaller element, then also we will stop, and in case you have equal element, then also you will stop. So here we are finding the equal element, so you will stop here. So now here I and j has stopped at the same, I has reached to this position and j is here. Let us check the condition whether I is less than j or not. Here I is the index number 1 and j is at index number 0. So I is not less than 0. So what we will do? We will exchange jth and the pivot element. So, this is the jth element, exchange it with the pivot element, it means exchanging this element with itself. If we are exchanging this element with itself, it means this element get fixed. We do not have any element on the left hand side, so 0 elements will be there on the left hand side, but on the right hand side we have n minus 1 elements. Okay. So, what we can write about the recurrence, in case you do the second iteration or you pick up this part, if you again do the partition, then the position of this element will get fixed. When you again do the partition with this one, the position of this element will get fixed. So, it means that if you have started with the n size array, the partition says that there are two parts coming up, one part contains 0 elements and the other part contains n minus 1 elements when you perform the partition. So, this will be the recurrence for such a situation, and when you will solve this recurrence, you will actually find that the complexity is n into n plus 1 by 2. We will solve this after some time. If the complexity is n into n plus 1 by 2, that means this is n square by 2 plus n by 2, it means this will actually be approaching n square. So, this actually is the worst case of quicksort, wherein the complexity is order of n square. Now, let us take an example wherein we have the keys in the descending sequence, the keys in the descending sequence. So, if the keys are in the descending sequence, let us fix this element as I, and here we have a j, let us take a pivot element as 100. Now, you increment I till you get a larger element than the pivot. So, this is not larger, this is not larger, no element is larger, only the infinite element is larger. So, you stop here, and then you decrement j, j comes here, 10 is smaller than the pivot and you stop here. Once you stop here, then I's position is 10 and j's position is 9. So, I is not less than j. So, we will exchange j and the pivot element. So, we will exchange 0 index element with the 9th index element. So, we get 10 here and we get 100 here, and the position of this element get fixed. The rest of the elements are like this. So, since the position of this element has got fixed, you will actually deal with this part of array and right part will contain no element. Now, let us set this element as I and this element as this element as j. Why we are setting this element? Now, 100 is being treated as the infinite here. So, you increment I stops here because this element is larger than 10, which is the pivot element. You decrement j stops here. Okay. Now, j will not stop here because this element is not smaller. J will not stop at 30, j will not stop at 40, 50, 60, 70, j will stop at index number 0. So, now in this case I is not less than j, you can see that I has exceeded j. So, what you will do, you will exchange j with the pivot element, it means you are exchanging first element with itself. When you are exchanging the first element with itself, the position of this element get fixed. There are no element on the left and there are some elements on the right. So, you will deal only with the elements which are on the right. What is the nature of the right hand side elements? The elements are this, these are elements in the descending sequence. You will once again perform the same operation here and the position of the last element will get fixed. Next time what will happen, the position of first element will get fixed. So, one time the last element is getting fixed, another time first element is getting fixed, next time the last element will get fixed, another time the first element will get fixed. So, it will actually be, it will keep on repeating. So, once again you will be finding that to solve this n size problem, the two partitions look like this once you have done the partition. When you will solve this, you will once again observe that the complexity is n square. So, here we can say that if we have the ascending sequence numbers or we have a descending sequence numbers, the worst case of quicksort is appearing that has order of n square complexity. Now, suppose our partition is taking place not in the mid, not on the extreme left, not on the extreme right. So, let us say we have an n size problem and this n size problem has got divided into two parts in which the left part contains n by 3 elements and right hand side elements contain 2n by 3 elements. Another case would be maybe that you find n by 4 elements on the left hand side and you get 3n by 4 size elements on the right hand side. Another case may be that you are dividing this, you are finding 1/5 element on the left hand side and then you are getting 4/5 element on the right hand side. Okay. The extreme condition, or there may be other conditions also wherein you are getting 1 by 9 elements on left hand side and 8 by 9 size elements on the right hand side. So whether this is the case wherein you divide the element into the equal size n by 2 and n by 2, or 1 by 3rd part and 2 by 3rd part, or 1 by 4th part and 3 by 4 part, or n by 5th part, and means 1 by 5th part on the left and 4/5 part on the right, or 1/9 part on the left and 8 by 9 part on the right, the complexity of quicksort will be n log n. It means in case you are able to divide your array, into 2 parts, the complexity will be approaching to n log n. But in case this condition happens wherein the left part or the right part does not contain any element, you are remaining with only one part. You see that Tn is equals to T0 means no element on the left, but some elements on the right. Similarly, in this case also no element on the left and n minus 1 element on the right. It is the partition from the extreme left and extreme right wherein actually the partition is not taking place, we are fixing a first or the last element. So the condition where the partition is taking place from extreme left or extreme right, that is the worst case, whereas in case we are able to divide our array in any of the 2 size problems that has the valid number of elements, the complexity will be approaching to n log n. So we can say that the average case of the quicksort is theta n log n. On an average this will be happening. Now let us say we have the extreme left or extreme right conditions. In case we have the extreme left and extreme right condition, you can actually stop the extreme left and extreme right partitioning being happening by the help of one is the randomized algorithm, where you choose randomly one of the element as a pivot, not as the first element as a pivot, but randomly any element in the pivot. For example, you have 50, 40, 30, 20 and 10. So you randomly choose any of the element as pivot. Let us say we have selected 20 as a pivot. So then exchange this 20 with the first element. So 20 is here, 40 is here, 30 is here, 50 is here and 10 is here. And then you start partitioning. When you will start partitioning now, then you will be finding 2 parts. So this is random selection of the pivot element. So every time the partition is going to take place, you randomly select one of the element as a pivot and you exchange that with the first element, and then you go with the partition, the usual partition method that you have learned. Another thing could be, or another method could be, that you take the median element as a pivot. It means let us say 30 is taken as a pivot. You exchange this 30 with the first element. So 30 is here, 50 is here, 40 will be here, 20 will be here and 10 will be here. Now you have selected this median element and you exchange that with the first element. Then you perform the partitioning with the help of this element taken as the pivot. In this case also you will observe that you will be finding 2 parts of the array. So we can control the worst case being happening with the help of selecting the median element as a pivot or random element as a pivot. Now let us think about the space complexity of the quicksort. In case we are getting the equal partitions or we are getting the equal size partitions, so total time the operations are performed will be, or total time the quicksort being performed will be log n, in fact 2 into log n, and as many times there will be the activation records being maintained in the recursion stack. So the space complexity will be dependent on the number of activation records pending at any moment. So if you are considering that log n activation records are pending at any moment, so C into log n space will be there, which can be written as log n space complexity, which is the best case, and on an average also log n will be the space complexity of this algorithm. But in the extreme left or extreme right partitioning, there will be so many pending record here. You will be calling the function like this, and there will be pending activation records in the, and so on and so forth. So total of n pending activation records will be there on the recursion stack, and the worst case space complexity of this algorithm will be order of n. So let us do the analysis with the help of all the sorting techniques that we have studied till now. The quick sort is actually getting a good good time complexity, but in the quick sort worst case may appear. We have learned how to control the worst case. In the quick sort, the space complexity is less than the merge sort. So it is a better algorithm than the merge sort in terms of the space complexity. So thank you.